In this video, I'm going to walk you through the first section of AP chemistry, which is basically just a review of many different topics from honors chemistry, including sig figs, dimensional analysis, conversions, density, matter, trends, and nomenclature. So I'm not going to go through all of that in this video because you can go back and review the honors videos to review those particular topics. In this video, I'm just going to go through the topics that are new or different from honors. So don't just watch this video thinking that this is everything from this section. You might have to go back and review certain videos on some of those topics depending on how strong you are. So after you look through the topics and see what they are, you might have to go back and reference them. But in this video, it's only going to be the new stuff that is different from honors. All right, so just keep that in mind. This is only the stuff that's different from honors, but you definitely probably need to review some of that honors content. Most of the stuff in section 1 is a review from honors, and we don't even really see our first new topic here until we get to the trends. So it's kind of a later part here of section 1. The first thing I just want to point out on this slide, this is the exact stuff we talked about here in honors, the factors that influence the periodic trends on the table. And we said that there are 3 factors here that primarily influence what's going on with these trends. But one thing I want to point out is in honors, we might have just called nuclear charge, but in AP, we really want to get used to calling it the effective nuclear charge. And you might see it listed, you never know if you can see it listed as Z. EFF, that is the same thing as saying effective nuclear charge. So you got to get used to using the proper vocab here. You cannot just say the nuclear charge, you have to say the effective nuclear charge. So we know that as you add protons here to the same energy level, the effective nuclear charge, or how strong the nucleus is, always gets greater. All right, so as you go across the periodic table, you're adding protons to the same energy level, so your effective nuclear charge gets greater, which basically means your nucleus is pulling in those outer electrons a little bit more, and this leads to a lot of different things here. So just get used to calling that the effective nuclear charge. The next thing that's different is when we get to ionization energy. Obviously, you need to know all the trends, definitions, what happens across and down, and the why. But when we get to ionization energy here, there's some exceptions that we need to watch out for, and we actually need to know the AP explanations for it. We cannot use the honors level explanations that we did. So we have to kind of go through this stuff a little bit more, and there's even something else here that we didn't talk about that we have to make sure we understand because it's definitely a very AP level. So if you'll notice here with ionization energy, there are exceptions to the trend. Typically, as you go across the periodic table for ionization energy, as you go from left to right across the table, it should increase. And as you go down, it should decrease. It gets easier to remove an electron as you go down. It gets harder to remove an electron as you go across because the nuclear charge is greater. However, you'll notice here there are some exceptions. If you look at beryllium and boron and nitrogen and oxygen, for example, you'll see here as we go across beryllium to boron, it actually goes down, goes from 899 to 801. And same thing for nitrogen to oxygen here, goes from 1402 to 1314. It should go up, but it actually drops. So we need to talk about this a little bit and see what's going on. All right. Obviously, you still need to know that anytime you remove a second electron, it always takes more energy to remove that than it took to remove the first. And then when you go to remove a third, it always takes more energy than the second, and so on. All right, so that's the same from honors, but these exceptions and something with the valence electrons here, that's new. So we want to talk about that a little bit more here. Let's look at this first exception here, the beryllium going to boron. This graphic is pretty good because you know that going across the table, it should increase as you go across. And you pretty much see that here for any row. But you'll notice here as you go from beryllium to boron, basically group 2A to group 3A, all right, it does go down and then it does start to go back up. it should go up all the way across. And you'll notice that happens even as you go from magnesium to aluminum or calcium to gallium. Anytime you're pretty much going from group 2A to 3A, you see this drop even though it should go up. So something's happening here as you move from group 2A to 3A, and it's happening for all of them. So we need to look and see what's actually going on. So you have to look a little bit closely here, and you got to look at the electron configurations. So for beryllium, beryllium would be 2s2, right? So it would look like that. And then boron, all right, as you go into 3A, that's when you start to see the 2p here, or no matter which energy level you're in, the p block starts filling. So for boron, he would be in the 2p, and he would be 2p1. All right, so he has one electron here in the 2p. So why does it go down when it should go up? Well, you need to look at the definition here of ionization energy. Ionization energy is the amount of energy required to remove an electron here. All right, so basically what this is saying is to remove the electron for boron, it's a little bit easier to remove this electron from the 2p1 than it is to remove this electron from beryllium as 2s2. Even though the nuclear charge is increasing as we go across, and this should not happen, that's what actually takes place. So what's happening here is something we need to really pay attention to. There's something taking place here, and this is a pretty big idea. What we say here is that the s electrons penetrate the nucleus more. All right. Essentially, they are closer to the nucleus. All right. They are feeling the full nuclear charge of the nucleus, and they are held on to a little bit tighter. So as you go from the S's to the P's, this first P electron doesn't penetrate the nucleus as much as these s electrons do. So it's a little bit easier to remove that first p. And then notice as you would add the p electrons in for carbon, nitrogen, oxygen, so on, it just follows the trend and everything goes right back to normal. But when that first one enters, all right, the P sublevel there, it's a little bit easier to remove it because these s electrons penetrate the nucleus more and they feel the full effect of the nuclear charge more. All right. Again, this only happens when you're moving from group 2A to group 3A because that's where you see the first p electrons starting to fill in. And then after that first one is in there and you add the second, it just goes back to normal, and the s electrons penetrating the nucleus more doesn't have as much of an effect. So this is something you need to watch out for, and this is how you would need to explain that for any of these exceptions here that happen as you're moving from group 2A to 3A. All right, you have to understand this idea that the s electrons penetrate the nucleus more. Now we need to look at why there is an ionization energy exception for nitrogen to oxygen. All right, so if you look here, as you go from nitrogen to oxygen, it does drop a little bit. As you go across, it should increase. And you see the similar thing happening as you go from phosphorus to sulfur and so on. So there's something else happening here as you go from groups 5A to 6A. All right, anywhere there as you go from group 5A to 6A in a particular row, this exception kind of happens and it gets lower when it should be getting higher here according to the trend. So we need to look at why this takes place. And it's not going to be the same reason that we saw for beryllium to boron. Again, we need to look at the electron configurations here. So both nitrogen and oxygen would have 2s2. There's no difference there. But then they're going to be entering the 2p. So if we look at this for nitrogen, nitrogen would be 2p3. So according to Hund's rule, nitrogen would have one electron in each orbital. And then, so this is nitrogen. And then we have oxygen though. Oxygen would be 2p4. So oxygen would look like this. Hund's rule says one in each until you're forced to pair. So that's what oxygen would look like. So you can see here, this is not going to be the s electrons penetrating more as the explanation here, because this is not dealing with the S's. We're in the P block here when these exceptions occur between groups 5A and 6A. So there's something else taking place. Notice here, as you go from nitrogen to oxygen, nitrogen had one electron in each of the orbitals, but then oxygen is the first one where you start to see the pairing up. All right. And this would happen anywhere here as you go from 5A to 6A, as would go from the third P element to the fourth P element, you would start to pair up in that first orbital. So what we say is happening here is there's something taking place called electron-electron repulsions. All right. When that first electron pairs up, all right, it causes a slight repulsion. Think about this. Both of these electrons are negatively charged, all right? Even though they're spinning oppositely, all right, they both still are negatively charged and they do repel a little bit. All right. So what this is saying is oxygen drops a little bit in ionization energy, meaning it's a little bit easier to remove that electron than it was to remove this electron in the nitrogen. And why does this happen? Because it's the first pairing in the p orbital here. These electrons are paired up here for the first time in the p sublevel here in this particular orbital, and it causes an electron-electron repulsion. And therefore, this electron is a little bit easier to remove because it really doesn't want to be there. Okay, so you really got to think about this here. This doesn't happen with nitrogen because there's just one in each of the orbitals. But when you go from the 5A to the 6A, this would always happen. You have that first pairing taking up there in that first orbital in the P. So there's going to be some electron-electron repulsions taking place, which means it's always going to be a little bit easier to remove that paired up electron. Even though it should increase, it actually decreases and it gets a little bit easier to remove because of those electron-electron repulsions. So you need to be able to explain these exceptions here that happen for ionization energy, whether it's going from group 2A to 3A or group 5A to 6A, you have to explain them on an AP level. There's something else here with ionization energy that's new in AP. You can actually use ionization energy to see the number of valence electrons a particular element has, all right, by looking for what we call jumps in energy. So you would need to be able to see a series here of these ionization energies, meaning a first ionization energy, so you're removing one electron, a second ionization energy, you remove two, a third ionization energy, you remove three, and so on. So you'd have to be able to see that here. But if you look for jumps in energy, you can determine how many valence electrons a particular element has. So for example, if we just start by doing this by looking at beryllium. So we have beryllium here, all right? So we want to look at beryllium. And you can see here, the first ionization energy of beryllium is 899 kilojoules per mole, all right? So then the second ionization energy for beryllium, so when you go and try to remove a second electron from beryllium, it goes up, which is expected. It always should increase every time you go and take another electron away. It goes up to 1757, all right? But then notice, if you went and tried to take a third electron away from beryllium, it doesn't just, double like maybe we saw from the first to the second. It goes all the way up to almost 15,000 kilojoules per mole, all right? That's a big jump. All right, we kind of just like doubled and then we went, off the charts here. What that's saying is beryllium was, okay, gave up one electron. It took some energy. And then, okay, it gave up a second electron. It took more energy, which is to be expected. But then in order to give up the third, it took a lot more energy. That's trying to show there that beryllium really didn't want to give up that third electron. So that tells us here that beryllium was willing to give up two, but not the third. So beryllium would have two valence electrons. And if you think about it, if you look at the periodic table, find beryllium there. Beryllium's in that 2 plus column. He wants to give up two valence electrons. But once you try to take a third, he's no longer going to have that noble gas configuration. He doesn't want to do that. All right. So if you look for the jumps in energy, you can clearly see how many valence electrons here a particular uh, element has. So same thing. What if we looked at, say, magnesium? Magnesium, the first electron removed is 738. The second is 1450. It basically doubles. But then when you go to take the third, all right, it goes up to over 7,000. That's a big jump. Again, magnesium's in that 2 plus column. He wants to kind of give up 2 electrons. It's going to take some energy, but he definitely doesn't want to give up the third because he's got 2 valence electrons that he wants to give up, doesn't want to give up the third. So even something like sodium. Sodium, first valence electron is, about 500 kilojoules per mole. The second electron you try to remove goes over 4,500. All right, and that makes sense. Sodium's in the 1 plus column. Sodium has 1 valence electron, which he wants to give up, doesn't want to give up 2. So you can use this ionization energy information and figure out how many valence electrons a particular element has. And then sometimes you can even identify the element from this depending on information that you're given in a particular problem. They might tell you the row you're in, the period, and then you can kind of figure out which element you're talking about based on this ionization energy information. This picture is pretty good because it shows the valence electrons here. So if you notice, we got sodium, magnesium, aluminum here. Sodium is in the 1 plus column, has 1 valence electron. So you can see the value here for taking away or removing 1 electron for sodium. And then boom, look at the jump in ionization energy. That tells you sodium does not want to give up 2. Willing to give up 1, has 1 valence electron, but does not want to give up 2. All right, we can even look at one we didn't look at yet. Look at aluminum. If you find aluminum on the periodic table, aluminum's in the 3 plus column. Aluminum has 3 valence electrons he wants to get rid of. So notice the first 3 ionization energies for aluminum, it increases from one to the next, but you don't see a massive jump until you go and try to remove the 4th valence electron. Aluminum has 3 valence electrons that he's willing to give up, but not the 4th. So just be careful here. When you see the jump in energy, so you see it from the 3rd to the 4th, that means that aluminum doesn't want to give up the 4th. Willing to give up the 3, but not the 4th. So you must have 3 valence electrons. Definitely this is something you need to be able to understand and you need to know for AP. The last thing in this section that is different from honors are the hydrates here with ionic compounds. We might have talked about these in honors, but I just want to kind of refresh in case you forgot about them. So anytime you have a ionic compound, remember ionic compounds have a metal and a nonmetal in them. If they have water with them, they're called a hydrate. So you would need to follow all previous ionic naming rules to name a hydrate. All right, so you still got to know your ionic naming rules, but then the key here is you would attach the correct prefix to the word hydrate to indicate how many water molecules are present, and you would put this right after your ionic name. So you would name it according to ionic rules, and then you would have some type of prefix with the word hydrate after the name to indicate how many water molecules are present. So you need to know these prefixes. They do follow the same prefixes as covalent. So it's mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. So these are slightly different from the organic or the hydrocarbon prefixes, but they're the exact same prefixes that you would expect for covalent naming. If we just want to try 2 of these real quick, you're more than welcome to, pause the video, try them on your own, see if you got the same answer, or you can just kind of walk through them with me. So the first one here is CuSO4, and then you see the 5H2O. It's like times 5H2O after it. All right. So the first thing I notice is this is an ionic compound. There's a metal. Non-metal looks like there's a polyatomic in it. So I have to follow the rules here. So the first thing you would do is when you're naming an ionic compound, you ask yourself the question, is the metal multi-charged? The metal is always written first. Cu is in the D block, so he is multi-charged. So as soon as you know that the metal is multi-charged, you got to crisscross the subscripts and make them your charges. Again, you can write this out. Don't try to do this in your head. So the Cu would be sending a 1 up to the SO4, and the SO4, that 4 is part of the SO4, so it's sending up a 1. Remember, you can't touch that 4 because that's part of the polyatomic. So when I rewrite this, I would have Cu getting the 1 plus. Remember, it's plus because it's the metal. The SO4 would get the 1 minus. The second step here, after you crisscross up, is to check the charge on the anion. So is that the charge of SO4? No, it should be 2 minus. So you make it correct. And you say, okay, what did I multiply 1 minus by to get 2 minus? I multiplied it by 2. So I got to do the same thing over here. So it's going to be 2 plus. And now you're ready to name it. You name the metal here. So it's copper, followed by his charge in parentheses is a Roman numeral, 2, followed by the nonmetal IDE ending, but this is a polyatomic, so it keeps its name sulfate. Copper 2 sulfate. But then you can't forget this water part. So it's times 5H2O. The prefix for 5 is penta, and then you add hydrate. So it's a pentahydrate. Copper 2 sulfate pentahydrate. All right, so try the next one on your own. Pause the video right now. When you rejoin, you'll see the correct answer. So pause the video and try it. Hopefully this is the answer you got here. Lead 2 perchlorate trihydrate because of the 3 water. It is multi-charged, so you have to follow the steps, and you do need the charge in parentheses as a Roman numeral. So that's how you would do naming with hydrates in case you forgot. You also need to be able to do formulas here with hydrates. Again, they have water in them, so you would follow all previous ionic rules, and then just remember here the prefix that's in front of the word hydrates tells you how many water molecules you need to multiply it by in the actual formula. So we can do this one together here. Write the formula for iron 3 chloride hexahydrate. So remember the steps for ionic, once you know it's ionic, metal, non-metal, it's symbols, charges, crisscross, simplify if you can. So again, you can feel free to write this kind of somewhere. Don't try to do it all in your head, but we write the symbols. So iron is Fe, chloride is Cl. Charge on each. Iron tells you in parentheses it's 3 plus because it's a metal. Chloride, when you look it up on the table, is in the 1 minus column. All right, so we wrote the symbols, we wrote the charges, and now we crisscross down. All right, if you can do that in your head in AP, feel free to do it in your head. Just don't get it wrong. But if you need to write it out, write it out. So when we rewrite this here, we're going to have FeCl3. So we have symbols, charges, we crisscrossed. You can't simplify. So don't forget the last part. Some people, get so excited that they wrote it correctly, they forget the hexahydrate part here. So this would be times, and if it's hexahydrate, hex is 6, and then the H2O. So FeCl3 times 6H2O would be the correct formula for iron 3 chloride hexahydrate. So remember, this video just goes through pretty much all the stuff that was maybe different from honors or some of the newer stuff here for AP. You still need to go back and look over all of the information in this section. And if you need to, go back and look at those videos from honors so you can refresh your brain on all the topics here.